chapter 14, we're going to do statistics. So if you're thinking about statistics, it's really, here we go, it's really the study of data, the study of information. We call information data in statistics. Typically, we talk about analyzing data and summarizing data and all sorts of things like that. So you collect information about whatever it is you're interested in, and you do a number of things. Well, once you've collected the data, you find ways to display the data. And so that tends to be charts and diagrams. So that's going to be the first thing we'll look at. There's quite a lot of the different ways that can happen. You summarize the data, make a summary of it. And that tends to involve things like calculating the mean, or a guy called the standard deviation. There's lots of them. And then there's a third branch, I guess it's called inference, just a fancy word. Inference means you make some kind of conclusion on what the data is telling you. You see things like, well, this data is strong evidence that something's true or something's not true, or this information helps you decide whether a new treatment is better than the old treatment, right? So your inference is your conclusion based on the data. Right? What did the data tell me that was useful, right? If anything at all? So let's look at some of the types of ways in which data can be visualized. Most people, human beings at least, don't like to see a big pile of numbers because you can't really tell anything much when, you know, suppose I collected data on the ages of 500 OC students. If I just gave you a piece of paper where the ages were written down and said, here we are, I've collected the data, you would look at that and say, I can't tell a darn thing. All I've got is a whole load of numbers, right? Don't we need some way to collect it, to display it, to organize it, whatever word you want to use, so that we can see something, right? So we can get at least a vague idea of what's going on. So have a look at some of these guys. These are straight out of the homework. This is a line graph. It's basically you have dots joined by lines, and this red one is a guy called Herb, and this blue one is a person called Lisa. And I can look at this in lots of different ways. And they ask you a couple of questions, which is fine, and we'll do them. But when I look at this data, I see some things and I think to myself, why was January, February, why was April such an expensive month for Herb? Why was he doing a lot of expenses? And why are these quiet? And then why is this expensive? So if you look at patterns, you can see things like something big has happened here. He spent a lot of money, but even more money in October. And it might be very good reasons for it, but at least I can see it now. If I look at Lisa's, she has good and bad days, but really for Lisa, it's probably, you know, that's the month that she spent the least. So if I was just vaguely describing this, I would say that Lisa was pretty consistent with her expenses. In other words, she did vary a few, you know, a couple of hundred one way or the other, but she tended to keep within quite a narrow band. On the other hand, isn't Herb all over the place? Can you see some months he shot up to, what, $400, and other months it was $50, right? It might be just the way that both of them do their job. Maybe they're salespeople and sometimes they cost more money. But you can answer questions like, during which month did Herb incur the most expenses? Well, he's the red guy, and that is October. So I go here, and I would say October. And when did Lisa get the least? When did Lisa get the least there? That was August. So can you see visually that line graph allows you to look at a year's expenses for two people and kind of compare and contrast them. Visually, it's a lot better. The other way of doing that, can I just do Lisa a big load of numbers, Herb another big load of numbers, and you just have a list of numbers, and you might not notice it, I would think. Here is a graph depicting the United States trade with Canada over various years. This is, well, it's given various names. I know it by a double bar chart, but you might hear it called something else. Basically, these are bars. It's a bar chart. And the light blue one is America, and the blue one is Canada. And these are various years going up in fives. Okay, what can I tell looking at this before we look at their questions? Right. Which country seems to be winning the trade deal here? Who sells more stuff, Americans to us or them to us? Right, Canada to America or America to Canada? Who's winning the deal?
Canada is.
Yeah. If you look at this, this is in terms of what we do. The United States imports from Canada the blue, the dark blue, and they export to Canada the light blue. Now, when you do a comparison, do you notice that the dark blue, no matter which year you pick, is always bigger, which means that we import more, right? We buy stuff from Canada more than we sell it. And you might think, well, Canadians, you know, that's okay for us. The Canadians might not like it, but that's good. That's not actually necessarily a good thing. Because you have to pay the Canadians for everything you buy. And so if you ever hear terms balance of trade, that's what's going on here. Here's another one. The amount of electricity used in a typical all-electric home, okay, so there's no gas, is shown in this graph below. I'm assuming this is good data. Although I'm not quite sure how realistic this is. Okay. If this was Alaska, or it was Arizona, can you imagine that those distributions might be different? Right? Just keeping yourself warm or keeping yourself cool or whatever it might be. But okay, taking that in mind, right? So what we've got here is that in a typical month, we use 1,300 kilowatt hours. We're now going to be asked to calculate using the information in this picture. So I'll just pick one and show you how you would do it. Let's see how much is done on your refrigerator. The answer as a percentage is 19. And the kilowatts in this month is 1,300. So let me nip back to my whiteboard and figure out how many watts did your refrigerator use, or would your refrigerator use in a typical month? Well, simply it's just 19% of 1,300. The easiest way for me to do 19% is just turn it into a decimal. So 0.19, 1,300 kilowatt hours to 247 kilowatt hours. If this diagram, I'm going to return to it, if this diagram is accurate, which I'm assuming that it is, We spend a lot more electricity in keeping our stuff cold in our refrigerator than I thought we did. You agree that looks quite large? For me, maybe it isn't a surprise to you. I'm not too surprised about the heating and air conditioning. I imagine, you know, you spend a lot of energy, electric energy doing that. Your water heater, right, for your showers, but just over 10% of your power is used up on that. Here is a well-known university, and they looked at their graduates and what they were going to do. These are sometimes called pie charts. I guess because they look like a pie and you're cutting pieces out of it. And in this particular question, there are 1,500 graduates. So if I wanted to know how many were going to go and do stuff in the nuclear industry, wouldn't it be 5% of that number? Those who are going to continue and do a PhD would be 27% of that number.
So basically when we're doing it, we want to take the percent to a decimal and then multiply that by the amount that it gives us as their total. I'm just trying to make better notes for myself. Last time I couldn't read my own notes and it made it really, really hard.
So what you just said is a perfect sentence to write down in your notes, because I think you said it exactly. I couldn't have said it better. So in these kinds of questions, you take the percentage for whatever area you've been asked, turn it into a decimal, 0.18, and always multiply it by whatever the total happens to be in the story. Are we good on that?
Yes.
These questions I kind of like because they're not numerical questions. They're actually using or getting us to look at the way that advertisement people and politicians and people who want to influence us work. Here is a diagram that shows you the current potential for commercial forest growth, and here is a potential one. Now, decide whether there's something wrong with this graph. So this guy has a scale, and this tree goes up to the 44.9, so that's 44.9 cubic feet per acre per year. Okay, so in a forest, right now, they can get about 44, almost 45 cubic feet per acre of land, right? So when they plant the trees and they harvest them in 10 years, whatever it takes, that's what the going rate is. But with different trees or different management systems, planting systems, whatever you want to call it, it could have a potential to be this number. Yet there is something wrong with that diagram. Right, let's look at the numbers. 44.9, 74.2. Looks good. Visually, does the tree on the right look like it's only 50% bigger? Or does the tree on the right look more because they've used an area picture? Do you see, visually it looks more than just half as big. If you took this tree, wouldn't two of them fit inside that tree? Area-wise, not height. I agree the height's right, but if you put them, like cut them in and fill them in, wouldn't it be twice the area? That's what the visual problem is. If you want things to be heights, use rectangles. Don't use pictures, because if only the length is important, you won't see the whole data. There's something wrong with it. There's another one they didn't mention, which is almost not even noticeable. Look at the left-hand side. Does it start at 0? Watch, I'm going to show you a deliberate way to make you think something's more extreme than it is. here is the real data, right? So this is, I don't know, January, and this is February. And the numbers start at 0 and they go 5, 4, 3, 10, 2, 3, 15. And this guy is 14, and this guy is 15. Doesn't really matter what the thing is, but when you look at them, would you agree there's not an awful lot of difference? February is a bit bigger than January, but it's just one bigger. Here's January. Here's February. Doesn't February look like it's a lot bigger than January if you just don't pay attention to the numbers? Doesn't it look like 4 times taller? Do you see why that's the case? Because I started at a scale of 10. Vertical scales should really start at 0 and go upwards, because that's the only fair comparison, isn't it? Because if you decide to choose a different starting point, won't you exaggerate the difference in height? You'll make that difference look like it's a lot bigger. I mean, you can count it, you can see that the difference is only 4, right? You could count it here and it's only 4. But visually, it's all about visuals. I think the politicians call it optics. That's the jargon word. So it doesn't matter what the truth is, it's what the impression that you're getting across is. So, God, look at how bad the unemployment rate has gone up. Or look at how good the number of people taking vaccines has increased. This is the truth. This exaggerates the truth. So we should always be on the lookout when people do charts to watch out for things that are there designed to give you a false impression.
Isn't this go in with like what you were talking about before in one of our previous units about looking at how the numbers are actually calculated? The numbers are all true, but one is to give you this impression,
Yeah,
and this is to give you this impression. And so it's
yes,
based on how it's calculated. So this
Yep.
is just the visual version of that.
This is a very similar idea, right? We're doing it through graphs instead of through how we decide to calculate the rate of COVID or whatever it might be. And now we're moving on to the next phase. You can put data in the form of pictures, and it's really helpful to do so. But one of the other ways in which we collect data or use data is a thing called a frequency table. It's just typically the beginning of statistics, but it's still the case. So what you can do in this case is that you collect data, and I'm going to randomly just write down a whole load of numbers. 17, 18, 21, 15, 33, 62, 60, oh, darn it. Yeah, that'll do. 67 and 17, and I need some numbers at the front. 18, 15, and another one, 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's plenty, right? This data right now is jumbled up, right? It's the ages of people in a family, right? Weird family, but grandparents and parents, right? Everybody's living in a house. This is the ages of them. You start with the smallest number, which is 15, right? And then you basically look for everybody who's there. So there's one. Oh, so this here is the age, in this case, the story, and then you have another guy called the frequency. So 15, there's one of them, there's two of them, there's three of them. So you write down, there's 3 15-year-olds. Since there aren't any 16s, I won't write it down. I'll put in 17, and there's 1 and there's 2 of them. I'll put down 18 next, but there's only 1 of them. Used up. Who would be my next number in my frequency table?
21.
Okay, so, and I think there's only 1 of them. Then 33, there's only 1 of them. 62, there's only 1 of them. And lastly, 67, there's only 1 of them. Now, this is a very basic table, a very basic frequency table. But from jumbled up, when I've written it this way, do you get an impression of what the numbers look like a bit better? Can you see that we start off with quite a lot of 15s, right? There's 3 of them. And then there's a couple of 17s, and then 18, and then it goes 21, 33, 62, 67. Do you get a kind of feel that you understand these numbers a little bit clearer when they're organized in some kind of way? And that's the job of the frequency table, to take data and essentially organize it in a way that allows you to maybe see it a little bit clearer, right? So far, so good. Now, imagine that I had a whole load of data, which I'm not going to write down because it would take me forever in a day. And this table is going to be the height and the frequency goes here. And so I don't know what it is. I was collecting data on rabbits and I was measuring how long they are, I guess their height. And I got 11, I got 12, I got 13, I got 14. I'm going to go up to 17. And this one is going to be a little bit different, but only a little bit different from this one. So 5 of the rabbits for that one, 8 of the rabbits, 11 of the rabbits, 7, 3, 0, and 1. Have you noticed that in this table, this frequency table, although there weren't any numbers with 16, I still put it in. That is much more common. Frequency tables like this, even if nobody got the score, you would typically put the score in and write 0 beside it. Now, you don't always do it. If I try to do a frequency table with this one, where I put all the numbers in, wouldn't this table be 5 times bigger? And most of it would be zeros. And that isn't helping the issue. So you can see that sometimes you have to make an executive decision, and that is only put the numbers in that are there and count them. But in general, the more likely frequency distribution table is this fella here. Now, when I look at this, I can pick out quite a few things that I couldn't if it was just a whole load of jumbled up numbers, right? For instance, what is the most common height for a rabbit? What's the most common height based on this table for a rabbit?
13 inches, I'm assuming.
Yeah, because it's the one that happened the most often, right? Secondly, do you see that there's a kind of, if I turn it on its side a little bit, I don't know if that helps, but can you see the numbers start off low, then they get bigger, and then they tail off again? Can you see that? There's 5, and then it's up to 8, then it's up to 11, so that's about here, right? And then it goes down to 7, down to 3, and then, you know, almost nothing at the end. So you can also imagine what that data would look like if I took that data and I made a guy that looked like this. So height against frequency. And I'd start at 11, then I do 12, then I do 13, and I do 14, 15, 16, 17. And frequencies need to go up to what, 11? So 0, 2, 4, 6, 8, 10, 12. And a height of 11, there was 5 of them. So that would be here. And when there were 8, they had a height of 12. And then 11 for 13. So
start with you because I circled underwear.
14 is 7. 15 is 3. 16 is nothing. And 17 is 1. Now I'm shading this, and I don't know if that helps, but visually it helps me. Does anybody know what name you give to this picture? Starts with an H. You ever heard the name? Starts with an H. It's called, we call these guys histograms. So if you've got a frequency table, it's normally quite common to take the numbers in your frequency table and to just create one of these histograms. And it has the same information, right? It's the same numbers, right? It tells you everything that this does. But most people, if you visually look at this, can you tell a little bit more about what rabbits are like? Can you see that? Starting off, not so many at 11, but a reasonable number, building up to 13, and then drifting towards the end. You can see that 13 is the most common height. Can you see that 0 people had 16? So 16 is the least common height for a rabbit. So you can answer all those kind of useful kind of introductory questions where you get a feel for what's the data telling me? I mean, if you did a histogram, and I won't put any labels in it, but if you did a histogram and it looked like this, wouldn't that just mean, it's a whole load of randomness, right? There's no pattern going on there, right? There's no going uphill and going downhill. There's no trends. It's pretty random, isn't it? Kind of haphazard. And if you see something like this, you see a little bit more shape to it. You can get basic information, but still good. Now I'm going to show you a question on the homework where you're creating one of these tables. I'm just going to show you or tell you how I do these tables, because you know my scanning is horrendous, right? So if I'm doing that question, and this is me, I print that page out and I get my pen and I go to the first number, which is 72, and I go down here and I make a little check mark. And then the next number is 71, and I do a little check mark. And then the next, and as I do it, I cross it off, so I can't count it twice. Then I do 68, check mark, 69, check mark. Now, when I am finished, you do 1, 2, 3, 4. Do you know what I do when I get to 5 to make it easier to count when I'm finished? You ever seen this trick? I can't really do it on this, so I'll zoom back here. I go 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. Can you see when I'm finished, I now know that there's 6 of these, 3 of these, 2 of these, and 12 of that. And it's dead easy for me to count. Now, some of you are much better than me. And this is another strategy. It doesn't work for me, might work for you. The first height here was 63. They just scan through all the data and they count how many 63s that they get. Now, since you lot have got 2 good eyes, most of you anyway, you might be able to cope with that. Why can't I do it? When I scan, I miss a row and I go from row 1 to row 3 and I miss a whole load of data, right? I just ain't happening with my brain. Okay. If you were doing it the other way, you'd say, okay, how many 63s are there? You'd go 1, 2, 3. You don't need the sound effects. 4, 5. I think there's 5. I don't think I missed one. And you would do it that way. You got to figure out what you're good at and what you're bad at. If you can do it that way and you're fine, great. Now, you finish doing this table. And it's quite possible. In fact, I'd be surprised if it wasn't true. I'm just randomly picking a number, right? That there might be a 0 somewhere, right? There aren't any, let's say 69s. I can see there is, but let's pretend they're not. When you add up all these numbers together, shouldn't they add up to 30? So when you're finished the frequency table, the last thing you do is add up all your frequencies. And if it comes to 30, you just say, nailed it. If it comes to 29, which it frequently does with me, because I always seem to lose one, you got to go hunting for the guy you've missed, right? You've missed one. Okay, so that is one way of doing a diagram. It's called a frequency table, and the other thing's called a histogram. The next one, I am going to use you lot. Oops, hit the wrong button again. First, I'm going to collect data, if you're willing to share. And then I'm going to create from it a diagram, which is called a stem and leaf. I'm glad they called it that, because I was checking what they did call it. Right, so here goes. You're going to tell me your age, and you're going to be honest. So you're not allowed to be my sister Morag, who once she reached 30, she was 30 something. And she was 30 something until her first boy reached 30. And then she stopped having an age, right? So if you're going to tell me your age, you've got to be honest, right?
I'm sorry, Professor. Can we see what you are writing right now, please?
Oh, all I'm writing is the word stem and leaf. And in a few minutes, I'll be writing the data that you're giving me. And I'm going to show you what that is. So I'm sticking in 65, right? So I'm committed. Shout out your age if you want to do your age. If you don't say nothing.
19.
Okay.
31.
41.
18.
28.
I heard an 18. Gabriel, I didn't catch yours. Gabe?
I was 18. I think the other
Oh, you
person
were 18. Who was the other one then?
28.
28. Okay. Is that 2 28s or just 128?
Just one.
Just one, okay. A couple more. I really could do with 4 or 5 more.
32.
32. Chuck in your partner or your big brother or something. That'll work as well. So if you know some other ages, just chuck them in. I need about 4 more.
7.
Okay. Oh,
29.
okay.
48.
48. One more.
19.
19. Let's see. 2, 4, 6, 8, 10, 12. That's good. That should be enough. Hopefully.
41.
Oh, too late. You missed the last call. But thank you for taking part. Now, how does a stem and leaf work? Well, if I tried to do a frequency table with this, the 2 versions of the frequency table wouldn't be very useful. The first version would be just to write down the ones that are there and leave gaps. But that isn't really very good at telling what kind of age distribution it's like. And the second one is to do all the numbers from 7 to 65 and have lots of zeros. Well, that's not going to work because it'd be a huge table with a lot of nothings in it. So the stem and leaf is a kind of compromise to that. So what you do is you have a guy called the stem. Now, in this question here, the stems are going to be the teens. So I'll give you an example of what I mean. If you did somebody who's 31, they would be 3/1. If somebody was 53, it'd be 5/3. So in a stem and leaf, you draw a big line like that, and we'll start with the smallest, and that's going to be 0, and then 10s and 20s and 30s and 40s and 50s and 60s. So this number basically means 60 something, 30 something, 20 something. So I can now go and say 65, 19, 31, 41, 18, 28, 32, 7, 29, 7, 48, and 19. And that's a stem and leaf. Now, if you look at that table, you should be able to take what's written here and figure out what the original data is. So for example, just at random, do you see this guy here? How old was that person?
48.
Right. And that person there, would you agree that person is 19? So haven't I taken a whole garbled up set of data and haven't I organized it in a nice kind of systematic way? And if I turn this thing slightly on its side, do you get a kind of impression of what the histogram might look like? You see, visually, it's quite an appealing way to do something. And this diagram is called the stem and leaf. And when you do such a diagram, you have to give a key. So you take a random number like 2/8 and you say that means 28. And the reason you need to do that is because can you imagine my data was 6.5 and 1.2 and 1.9? In that case, wouldn't 2/8 represent 2.8? So you need to know what the stem and leaf data represents. So you need a key. And I just noticed something that I need to do here. I did something. There's a slight difference between this data, right, this stem and leaf, and this stem and leaf. Did you notice what the change was? You should put your stem and leaf in order. So if you've got like 4 or 5 digits here, like 78, 772, you should put them in order because that's part of the organizational process. So imagine I have a stem and leaf and it was to do with results in an exam. And it looked like that. And my key was at 6/3 means you got 63 in the exam. Then this stem and leaf, you should be able to look at it and tell all sorts of things. For instance, isn't the most common score 50 something? Would you agree there are more 50 somethings than anything else? If I turn it slightly on its side, do you see it as it kind of goes uphill, goes downhill, kind of looked at? If I said, what's the highest score? Somebody got 82. This is made up data, it's not this class. Wasn't the lowest score 31? Can you see this stem and leaf has everything that you would have got if you had a big list of numbers like this? But isn't this much easier to visualize and to suck out patterns, special cases, all that kind of thing? Do we have any questions about that? Are we comfortable about this new guy called the stem and leaf?
Can you do just kind of a quick over on
Can I do?
the different, yeah, because on the other one I have it all written on one page so I can like see how it went from one to the other, but I feel like I'm kind of confused on where we, because we went from this to this, and I want to make sure I know how to do it.
I'm trying to think of this to this, what we're getting at. So I have this data that became this stem and leaf,
Oh,
and then it turned into this stem and leaf. It's the same data. The only difference is I put them in order here.
Oh, okay.
And if you
I
look at it,
missed that
that's
somehow. Okay.
Okay, so that's all that was. That's all that the difference between from here to here was. And so when you're building stem and leaves, you might want to do a kind of rough and ready version where you're not particularly neat. And then once you've got the major data analyzed, you then draw a nicer, neater one, and you put them in order while you're doing it. And typically it shouldn't be too hard to do that. So any questions? Any more questions, I should say? Are we good? I mean, one of the nice things about 107 is how different the topics are. I think
I'm so
that's
sorry, Professor.
kind of cool. Say that again, I didn't catch that.
I cannot understand.
You like different.
Where did you get those numbers?
Is it the last diagram?
Yes, I mean 1, 2, 9.
Right. These numbers here?
Yeah.
Oops. Wait. Now let me point at it. There.
Yeah.
These numbers here?
Yeah.
These were just made up. I went and said, pretend exam marks, scores. So I made up a story, and this is the stem and leaf that I got from this made up exam. So these numbers just came out of the blue. I just made them up. It's just so that we could show you another example of a stem and leaf without going through all the trouble of writing down data and then converting it. So it was just a convenience. So these have nothing to do with that. These are two totally separate questions.
So we're just counting those like a frequency of numbers or what?
Well, what we're doing is it's each one of these is a specific number. So that's 31. That makes it, that number there is 32. This one here is 64. This one here means 82. So these are not frequencies. These are actual individual scores. Each one of these numbers is one particular score that one person got in a test. It's not the same as this 5. This 5
I think
is a
what
frequency.
she was asking, because on ours it shows like the weird chart and it has all the numbers down it. And now that you're saying that, that makes sense. So it says 1, then I would say like on mine I have 19 and 17. So I would put 7 and 9 to represent that is. I don't need to put 17 and 19 in column 1. I just put the second number.
Correct. I tell you what
Okay.
I'll do. I will go in and
I was trying to figure that one out too.
okay. Zoom's just been a pain in the butt right now because I've got too many windows open. So I'm closing the participating window and I'll open this window and I will do this window and then I'll open this window. Whew. Okay. So Hopefully you're looking at question 8, which is draw a stem and leaf, right? So this number here is 27. That means you put a 7 here. This number is 50. So you put a 0 here. This number is 26. So you put a 6 here. The next number is 18. So you can put an 8 here. Can I just randomly put digits in just so I can, because it'll take me forever to do this by hand. Can we pretend that this is real data? Right, so don't say where did that 39 come from, because the answer is I just made it up. Right, let's
Okay, so-
pretend. So I'm just pretending that's the right numbers. The reason I want to do that is once you've finished your stem and leaf, do you notice that some of your numbers are not in order? So this 27 and 26 should be 26 first and then 27. You see this guy? Well, actually, that guy's in order. Darn it. Okay. There. Let's put another number in.
Ascending order, right?
Yeah. Yeah. So suppose you had this guy. Wouldn't you have to rearrange it and have that guy? So your stem and leaf has two features. One is the numbers are in order. And the second one is that every number gets represented by its second digit. So 60 gets represented down here like that. And what
If
else?
there's not a number in there, then you don't want to put 0 on this one.
No,
because that would
if
mess
there's
it up,
nothing there, you're right. You just leave it blank.
right? Okay. That makes way more sense. I was trying to make that make sense with what you drew, and that was not making sense.
Okay, are we clear on now what we're getting?
No,
What?
but not clear.
Not clear?
Not clear.
Okay.
I don't understand why do we need to divide those numbers in such a manner? For what is the purpose?
The purpose is so that we can visualize this data. Putting it into a table or a chart in this case helps us to see what the range of numbers are like. It helps us to see if there's a pattern. Did they go up or did they go down? It's a way of visualizing a whole set of numbers. Right now, there's a big set of numbers here. If I said, is there a trend in those numbers? Right? Do you start off young and then a lot in the middle and then it dries off? Are they random? What age group's the biggest, right? Is it 40s or is it the 20s? You know, questions like that, you can't really answer easily if all you've got is this fella. But if you make one of these stem and leaves, and I wish now I hadn't rubbed that out, but if you made one of these stem and leaves, you can put that data into a format that allows us to
So
visualize it.
will you check and see, because it says enter none. Oh, never mind. It says I just found a thing. So actually, if there's none on there, you have to write none. I'm like,
Oh, okay
I
then.
was trying to get it
I'm
done, but it
following their
actually
instructions.
enters it. It says enter none for stem values if there is none. That way you don't
Right.
confuse the zeros.
If you were doing
Yay!
it physically on paper, you would just leave it blank. But for WebAssign, for whatever reason, it physically needed you to say none. But if you left it blank, it would obviously mean none in real life. But that is it. So
Okay,
your question, Naja.
and the order of numbers should be ascending, right? Like a bigger and bigger, right?
Yes, small to big. Yes.
Okay.
Right. Now, here, I'm going to have to shrink this thing down, unfortunately. Here is our next question, where we've got a particular shape called a bar graph. Now, if you look really carefully, do you notice that each rectangle has a tiny little space between it? You see the gap between this rectangle and that rectangle? There's a little gap.
Mm-hmm.
Yeah, that's what makes a bar graph. That's one of the features that makes a bar graph different than a histogram. Remember when I drew the histograms, they were all stuck next to each other, there wasn't any gaps. But a bar chart, one of its features is always has gaps. The second thing that makes a bar graph different from a histogram is, do you notice at the bottom, it's not numbers, but things. So it could be red, blue, green, yellow, right? It could be old, young. It could be Republican, Democrat. When it's a histogram, isn't the horizontal, the bottom 15, 16, 17, right? 82, 90, 95, right? It's numbers. So when you're looking at a diagram, you should be able to tell when you're looking at a bar chart and when you're looking at a histogram, although they're pretty much ways of organizing data. So let's see the story. The number of trucks from 3 automobile manufacturers that are still on the road 10 years after they were originally made and sold is the following. Brand A, 97% on the road, brand B, 96, and brand C, 95. And draw a bar graph. So there are 4 guys here. Only one of them represents this data. So what am I looking for? I'm looking for a 97, a 96.4, and a 95. Okay. Now, my eyesight's not great, but would you agree the rectangles are all the same height?
Yeah, it looks like all the same.
Looks like it. Would you agree that this one has a little bit of fluctuation?
Yes, it does.
And it's a little bit lower, a little bit bigger, a little bit lower. Now, but yeah, question? But I'm not picking this one because shouldn't brand A be the tallest of the 3 and it's not the tallest? Why should it be the tallest? Because it's got the biggest percentage. So I'm not picking that one. And this one is the biggest. That's right. This one's a little bit less. And this one's a little bit less. Does that follow 97, 96, 95? Yes, it does. It's that one. Did you see how I figured out which one of those 4 pictures represented this data, the 97, 96, 95 guy? Because if you look really carefully, you can't tell what these numbers are. They're so close and it's hard to read. But can't you see big, smaller, smaller? And that I can see. Now, if you did a scale starting at 95, I'll have to shrink this down. One of these 4 guys would be the same data. It'll have to be this one. Which one of those 4 guys is the same data as the original? It went 97, 96, 95 kind of thing. Which one of them would be that?
Left and bottom.
Agreed. Big, 96 and a bit, 95 and a bit. Boom. And back onto charts. Now it's asking approximate, so we'll do our best to judge this. Balance of trade, that's exports and imports. So we buy more stuff, import it, than we sell to Mexico. And we're being asked to figure it out in the year 2000. So here's the year 2000. And this is a judgment call. I would say Mexico is about, what, 138? And the other one next to it would be 106. So I'm going to say it's 106.
I would say 110.
110? Okay. 110. And what about the top one then? 130 something? Call it 138. According to me, that's about 28. Well, I don't have a 28, but I do have a 25, so I'm going to pick one of those 2. And now we have to decide, is it negative or positive? Well, if you take this number and subtract the one next to it, because that's the order, right? What you buy, take away what you sell, it ends up being a negative number. And that is ended up.
The approximate balance. So
Are we good? Yeah, approximate. So 20 something, 25 would count. These questions take up so much room, which is a bit distracting for me to show you what's going on. But this newspaper article discusses whether Social Security could be cut. Offered the information shown is the figure below. Use the information to answer whatever the question is. So they have lots of different diagrams going out here. And they have a question at the bottom, which is pretty much an estimate one anyway. But I kind of like this picture, so I'm just going to focus on this one first. This here is information starting at 1960 and going into the 1990s. And the red line is, what is the red one? Collected? Yeah, the red one is the money that they've collected. And the blue one is what they've paid out. Okay. So, according to this anyway, doesn't the government collect, at least up to the 1990s, hasn't the government been collecting more than they've been paying out in Social Security? If we move on to these one, these taxes have increased. Social Security and Medicare taxes have gone up, and the income tax rate, at least up to here, has gone down. And then they hit you with this one. The reason why Social Security will probably be in trouble is because of the baby boomers. Anybody heard of the term baby boomers? Right? There's a big bump in the population caused by essentially when people came home from the war, they started families, right? And there was a big surge in children born in that 10-year period, right? 45, 55 kind of rate. And the result is that the number of people who are going to be collecting Social Security is going to take a sharp increase over the next 10 to 15 years. In that same time period, that 10 to 15 years, the number of people who are working and therefore paying Social Security will not increase by the same amount. So it's not like, oh, 5 more million people are getting Social Security, but that's okay. 5 million high schoolers have now left high school and are working and are paying into Social Security, right? It's a lot of people retiring and not that many coming in at the bottom end. And that's going to mean that this will switch. So unless the government decides to increase Social Security, which they have been doing here, in other words, you pay more of your salary towards your Social Security, or they decide to cut what they give you in Social Security. And politicians will tell you that that's never going to happen. But then politicians have told me lots of things that were never going to happen. And then they go and do it. And have you ever noticed that what they tell you before you elect them and what they do after you elect them isn't always the same? So don't trust the buggers is my advice. Because unless they do something, there is going to be a big problem. This one's just the same data. So my little word is that there will be, in my prediction, a Social Security payment problem. Now, they can fix it, but they better, because I'm relying on it when I retire, at least partly. And normally what governments do when they fix something isn't they basically just do some minor thing that gets them by this 2-year period so that they can get elected again. So I doubt if they'll do a major fix. They'll do minor ones. So
Can I ask a question, please?
yes, sure.
So those stems and leaves and I don't know, you call it diagrams, everything
Uh-huh.
we need is just to count them and to write down all those numbers, or like just calculate amount. Is it right?
Yes. So most of the tables are, here is a whole load of numbers and you count them and you put them into the table in different ways. And it depends on whether you're doing a histogram, a frequency table, or a stem and leaf, what you end up doing with those numbers. But they're very similar. You know, you count each one,
Mhm.
and then you can make one of these, or you take the data and you make a stem and leaf. Actually, wouldn't I be able to make a histogram from this stem and leaf very easily? But if I turned it sideways, haven't I done a histogram? Virtually. I wouldn't do it that way, but visually you could make it happen.
Okay, thank you.
So, next section. Let's suppose that we've collected the data, we've made nice histogram, stem and leaf, we've done all sorts of cool things. I'm now going to look at how do you summarize the data. And there are a number of different things that we do in statistics that allow us to take a lot of data and crunch it down into a few numbers. So the first kind of things are called mean. Another one's called the median. And the third one is called the mode. And the mean is what you get when you add up all the numbers and then you divide by the total amount of numbers. The median is the middle number, and the mode is the most popular number. Now, the guy that we call the mean, you would probably call him the average, wouldn't you? You know, if you said, what's the average of your 5 tests? Wouldn't you add them all up and divide by 5? Right. If I said, what's the average age of members of your family? When you take all their ages, add them up and divide by how many people in your family. And the median is the middle number when they're in order, and the mode is the most popular. Each one of these is basically trying to give you a single number that represents a typical person, or a typical value, because it might not be a person, in the data. So if you had, I don't know, suppose you did 10 quizzes, right, one a week in your English class. If you found the mean, wouldn't you add them all up and divide by 10? And if the answer you got was 7.5, wouldn't that mean that you typically got about 7 or 8 out of 10 in the test? Right. That would be an example of what we're doing here. So we are going to take some data. I'm going to make up some numbers and we're going to calculate the mean, the mode, and the median. So 1, 3, 3, 7, 8, 9, 10, 11, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n equals 10 just means there's 10 numbers in this data set. And I would like to calculate the mean. Well, if you want to do that, you add them all up. And you divide by 10. So 4, 7, 14, 22, 31, 40, 51, 64, 74, 83. So the mean would be 83. Are you happy about how you would calculate the mean? Right, you add them all up and divide by how many. I know you call that the average, or most of you call that the average, but it's better to call it the mean. Strangely enough, all three of these things are called averages. They're all different versions of an average. Each one slightly different on how it's calculated. Now the mean is the easy, well, the mean and the mode are the easy ones. So let's do the mode slightly out of order because it is typically relatively easy to get. If you look at this question here, and I said, what's the most popular answer? Would you agree that there's 2 3s and then there's 2 9s? Would you agree it's a kind of draw? Right? There were 2 3s in this data, there were 2 9s. Not a lot of difference, but the mode, and it depends on the textbook, the mode is 3 and 9. In other textbooks, the mode is that there's none in this question. Now, both are valid, but I prefer none. And you might say, well, but wait a minute, there's more 3s and 9s in any other number. Can't we call that the mode? It has to be one number that's more popular than the other. Let's be ridiculous for a minute. Can you imagine every single one of them was a different number, right? There were just one of each number. Would that mean that the mode was you had to write down every single one of them? Can you see that'd be kind of silly, wouldn't it? Second reason that I prefer this instead of that is any average, whether it's a mean, the mode, or the median, should be a single number that represents the typical. You can't have two things representing the typical person, right? It doesn't, logically, it doesn't make sense to me. So,
Okay, so I have a question.
Yeah.
So like on our homework, most of our questions have only have 5 numbers.
yeah.
So that would leave us always with one that's in the middle of the 5, right?
Oh,
'Cause
that is going to be for the guy that we call the median, yes.
So that's going to be the median.
Yeah,
So
the mode is the most popular. That's what I'm doing right now.
okay, so the mode, if there isn't anything that's doubled, then you would have none.
Correct.
And if there's more than one thing that is double, that still doesn't give you, you have to have one thing that has more than everything.
Correct. So let's give you some examples of modes with very small data sets.
Can I ask a question, please?
Yes. What's your question?
The question is about mode.
Okay.
If, for example, there will be more like number 3 or 9,
Yeah.
do we need to write down the most popular number or all of that more than that we can see more than once?
Right. I believe what you're saying. I'll show you in this example, and that may answer your question.
And I
So-
have one thing for mode on our homework, just in case anybody didn't notice it, they're doing the same thing like the none. And you have to put capital D-N-E if there's none, if
Okay.
nothing exists.
Right. And now
Oh,
you
we
said that, I wrote it down. Right.
I know.
So, right, Nadia, in this very small data set, would you agree that there's 2 number 3s? And isn't that the most popular number? So in this case, the mode will be 3. In this case here, every single number happened once, so the mode will be none. Now, you could get a,
For
you
example,
could get, yeah, you could get an example where this happened, right? And what I'm saying is, you say none when that happens. So you don't write those guys. So
Why
what I
not?
was saying up here is that there are some textbooks who say that you write down 2 different numbers. And I'm saying we won't do that. We will say none if that happens, right? So that's our rule. Unless there's one number that's bigger, more of them than anybody else, but just one number, that's your mode. Other situations ain't going to happen. Did that answer your question, Nadja?
I didn't understand why there is none where there are 2 3 and 2 5s.
Correct.
It's
So-
because
Mhm.
yeah, go ahead.
No, do it, Aubrey. You could probably say it better than I could.
It's because there's, even though there's more than 1 3 and there's more than 1 5, there's 2 3s and 2 5, which means that they're the same amount. So there's no more than 3 and there's no more than 5. So it means that there's none. There's no mode. You get it?
Right. So to be a mode, you have to be one number that's more than anybody else. You can't have 2 numbers drawing. That means none, right? You have to have one number
Question.
with lots more than any of the others.
Okay, it's supposed to be just one number.
That's
Yes.
bigger. Yeah, that's more
Well,
than
we
the other
can.
one.
Okay. Okay,
Now-
now I see.
There.
Thank you for that.
I understand.
Now we're going to do the one in the middle called the median. And the reason I kept that guy to the end is because he's typically the hardest one to do. So I'm going to do it with my data set, which is much bigger than the ones they've got. Looks like they've got like 5. Right, I've got 10 numbers here. Now, the middle number, right? The middle number. Well, if there's 10 numbers, shouldn't the middle number be the 5th one? Right, the 5th one along. 1, 2, 3, 4, 5. It should be that number. But if I count from this side and I count who's the 5th number, I get 1, 2, 3, 4, 5. I get this number. Do you see that there's actually, in this situation, aren't there 2 numbers in the middle? Right? Now, there are 2 ways we could have went. You could say, oh, they're just going to do that thing with the mode. You just say there's none. But they don't do it in this case. And sorry, that's the rules of the game. What you do when there are 2 numbers in the middle is that you call the mode. Well, what number do you think they would pick?
8.5.
You pick the middle of the 2 numbers. So that's why calculating the mode can be a little bit uglier, right, than other things, right? Adding them all up and dividing by 10, although it takes time, is not hard to do. Picking who's the most popular is relatively easy, as long as you realize it will only have a mode if there's one number clearly more than the other. But for the median, it gets a little bit trickier. So let me show you a different data set.
I'm sorry, I cannot understand. You wrote mode 8 and 9 or 8.9?
I didn't write either of those. I wrote 8.5.
Sorry. Looks like that to me.
Right, they are 2 numbers in the middle in this particular set, right? And the modes then is the average of the 2, right? The middle of the 2. So in the case here, the median is called, oh, shooting face.
Yeah.
I see what you're getting at. I have no idea where my brain was thinking. Yeah, that probably makes your life a lot simpler, Nadia. This is a new guy. This is the median that we've calculated. And the median is 8.5.
Yeah, also
Yes.
So it's something
Okay.
strange.
Let's look at a different data set. Let's look at a data set where there's an odd number, 5. In a funny sort of way, this is easier. Which number is in the middle?
21.
Which one?
21.
21.
Yeah. So in this case, the median is just 21. So when it's 7 numbers and 9 numbers, isn't there one number in the middle and that's the median? But when there's like 8 numbers or 6 numbers, don't you have to kind of do a kind of double take? Right, let's do another even one. Let's do 6. Well, if you do 6, aren't there 2 numbers in the middle? Third one along, right? So what number is the median now, right? It's the middle of the 2 guys,
23 and 27.
right? But a single number. So how do we find the middle number?
We divide 20,
Median.
27 minus 23, 4, 25. Is it right?
Almost, you subtracted, but you should have added. I think you said subtract. It'd be 25. Would you agree 25 is between these two? It's in the middle.
Yeah, I just subtracted it. Okay.
Yeah, adding is what you should have done.
So
we've got these 3 guys. Keep going.
we just add them and divide, right?
Yeah.
Okay.
If there's 2 guys in the middle, add them and divide. If there's
So
one
even
guy in
if
the
they're
middle,
far
you've
apart?
got your answer. Yeah.
So
Even
you
if
just always
one of
add
them's
them?
20 and the other's 30, yeah, it still counts as in the middle, right?
Oh,
That is really cool.
Now-
actually.
I would just count usually.
you like
I
that?
didn't think of doing that.
So what we're going to show you now is that you can actually get your calculator to do a lot of what I just did. The calculator can get you a median and it can get you a mean. It can't get you the mode. You got to do that the old-fashioned way. So I'm going to try and show you on a TI-84 how to calculate the mean and the median using your TI-84. Now, you don't need to do this because I've shown you how to do it by hand, but would you agree probably, especially calculating the mean, isn't it a bit time consuming because there's a lot of buttons to press? And it'd be nicer if you could do it in a shorter way. Are you looking at a picture of a TI-84 calculator right now? Okay, so it is a little bit, there's a lot of steps in this. So if you want to use your TI-84, you're totally allowed to. You might want to look at this video, pause it and rewind it and pause it and rewind until you've got the gist of it. So here goes. I'm going to make up a set of data and I'm going to calculate the mean and the median for it. So first thing you do is you hit this button called Start. So you hit the Start button. That's easy. If you're doing it with me, you can keep going. I'll write that down so that when I return to my screen, you'll see it. So you hit the Start button. You then choose number 1. It's called Edit. Actually, it's on number 1, which is nice. But see, if you had to choose things, you would move this around. But it's on 1, so you hit Enter. Now you should be looking at a table that looks just like mine. And you put the data
What number
in.
did we do when you got to the
Number
stat? Was
1.
it- Okay.
Start, and then I'll go back to the beginning. You go Start, number 1, Enter. Now, what we're going to do is we're going to put our data in, right? The numbers that we've got. So I'm just randomly putting them in. So I'm putting in 15. These numbers are just whatever the question happened to be, right? And you type in the numbers. And there. You pick any numbers you like, but I'm done. So whatever so a list of 10 numbers, you type in 10 numbers. So you then type in the numbers. So far, so good, right? Start, choice number 1, edit, type in your numbers. Hit start again. And now you're going to move over to this thing called calc. You see this guy here, calc? And you do it by pressing this key. Oop. So if I move it back, I move it forward. I move it back. You see that button? Now get to calc. Now that we're in the calc menu, choice number 1, variables. So choice number 1, variables. Oh, almost done. Now, I put all those numbers into a place called L1, didn't I? So I need to tell it where L1 is. I don't know if you can see it on this screen, but on your calculator, have you noticed that the number 1 has a blue L1 written above it? That's what I want. I want the blue number 1. And that's how you get L1 in. We're finished. All I do is hit enter. Now, there are a whole load of stuff there. And everything we want is here. It's just coded. See that guy at the top? It looks like this. An X with a little hat above it. That is the mean. And that is, in this case, about 31.1. Right now, don't bother about them, although we'll use them later on. If I hit this scroll down button, can you see this guy here called med? That's the median.
You're right, send that to me.
And median
What?
is 23.
What?
I am going to do a participation here and mute use. There we go. So did you see how the median is 23? So that process that we just went through allows us to get the mean and the median. So you hit start, you choose menu 1, edit, you type in the numbers you want in L1, you hit start, you move over to the calc menu, you choose option 1, you type in the blue button number 1, because that's how you get L1, and then you have your menu and you read off your answers. Now, although you don't need to do what I've just did for calculating means and medians, you will need to know how to do it for later calculations. So you might as well get used to it now. Right. So I'm going to do that same process again, and we'll do it from some new data. So why don't I collect some data that I already got from you, if I can find it. Bear with me for a second as I scroll through my multitudinous pieces of paper. And here we go, found it. I am I'm going to find the mean and median of our ages. And what that will tell us is the typical age of someone in this class. Right. So this is the data that we're going to put into this calculator, and we're going to calculate the mean and the median. So here goes. Okay, what? God, it's annoying when it does that. I hit a key and then it doesn't do anything. And then I have to hit it a second time. Okay, well, let's just get out of that screen. Right. So, hit start button. Number 1, edit. But I still have the numbers from my old question, and I don't want the numbers for my old question, right? I need them to go away so I can put in the numbers for my new question. And you can do that. Let me show you how you do it. Hit the up arrow. Do you see it's now on L1? See that? Then press the clear button and hit enter. Do you see how I get rid of that guy? Up arrow, clear button, enter. So I'm now going to type in all the ages, starting with me, 65. Then I did a 19. Then I did 31, 41, 18, 28, 32. Somebody threw in one of their kids. Then there was a 29. Somebody threw in their kid. Oops. Do that again. 29. Then the other kid, the other 7-year-old. A 48 and a 19. So you type in your data. Next, hit start button again. Can anybody remember where I go next?
Calc.
So you scroll over to calc and option 1. So press enter. Can you remember how you get the L1? What were the 2 buttons you press to get L1?
The blue button and the number 1.
Although it could be a yellow button or some other color in your calculator, but it's a blue button in mine. And the mean for our class is 28.7 if I round it off. And the median for our class is it's about 28.5. So let's talk about these 2 numbers before we move on. A typical person in this class is about 28. You agree? At least based on our data. Now, I'm old, I'm 65, right? And some of them were kids at 7. But in the middle, you're 20-somethings. That's reasonably accurate. Have you noticed that both these numbers are very similar? Right. That's not always the case, but in many situations, they are the same. So you might think, well, why do we need 2? And the reason why we need 2 is because sometimes the 2 numbers are really quite different. So I want you to imagine that we had some data and it looked like this: 5, 5, 10, 10, and 100. If I was asking you roughly, where is the middle? Right, what's a typical person or score? The middle number here is that guy. So the median is 10. if I calculated the mean, it would be 5, add 5, add 10, add 10, add 100. And that is 110, 20, 30. And that answer is 26. Would you agree that there's quite a discrepancy between these two numbers? Which one of those two numbers would you consider to be the more accurate? I would say the median. Would you agree most numbers are 10 or pretty close to 10? Wouldn't you say 26 was a bit in the big side? Aren't most numbers a lot less than 26 and only one of them is bigger? And the reason that we need two measures is because of the mean is can be changed a lot by just one big number. They give a good example of that when they do it in some classes I've seen. Imagine we wanted to know the average wealth of people in Washington State, right? So we went to Aubrey and we said, Aubrey, sell everything you own and tell me how much you're worth. And since Aubrey's a student, it's probably $2, right? And then you go to other people. I'm joking, Audrey. You could be a millionaire for all I know, right? But and you go to other people, and they're worth 50,000, right? So the wealth of a person is how much they would have if they sold everything they owned and paid off their debt, right? What would be left? For some of you, couldn't that answer be negative? In other words, you owe more money than you're worth, right? If you sold everything, you still wouldn't pay off your debt, right? If we collected that data for every single man, woman, and child in Washington State, do you know the answer would be something like $2 million? And you'd say, where are all those rich folk? Because I'm not one of them. And the answer is, it's not that there are a lot of rich folk. Do you know the answer is? It's Bill Gates and about 10 other people. Because isn't Bill Gates, even though he's divorced, his wife's got the other half, whatever you want to call it, aren't they together worth about $50 billion? Now you take $50 billion and divide it by everybody in Washington, can't we all end up being millionaires? Can you see how, well, it wouldn't be quite, but you know, if you added all the Bezos and the other couple of billionaires that we've got, couldn't they add up to a big chunk of money? And then you only need to divide it by 5 million and bingo, you've got it. So everybody could easily, on average, be worth 2 million. But there wasn't that caused by a few very, very large numbers. A better measurement of the average wealth of people in Washington is the median, which is basically, you can imagine everybody in Washington, theoretically, lining up in a big row with the people who are really in debt on one side and Bill Gates at the end. And you walk till you got to the millionth, the middle guy, and you said, how much money are you worth? And you'd probably get a realistic figure like, I don't know, $100,000. And that is the reason why we have two measures. And if you ever look at government data, they always use medians. They say the median household income, the median age, the median price of a house. Right? Do you know you could live in a street with 100 houses and all of the houses are worth $200,000, right? But one of them at the end is a special house that's worth $50 million. Wouldn't the average value of houses in your street be like $500,000? Only because that one big number. So they talk about the median house price, the guy in the middle. I guess the question might be then, why do you even have means? Well, means are very useful when they work. They're actually much more useful when they work than median is. Any questions about that? Right. So let's see if we can close off some windows and return back. Got to keep track of my time here. and look at some homework questions. And wonder if it's maybe my mouse. Maybe that's the problem. Yeah, it probably is my mouse. I'm blaming the software. Right. Here is a set of data, 6, 7, 8, 9, 10. So Tara was probably referring to that earlier when she said there's 5 numbers. Right, if you look at that data, what is the median? Because you should be able to tell just looking at it. What number is the median?
8.
And is there a mode?
No.
So you write in, so your answer would look something like this. 8. I think they want capitals, so I'll assume that that's what they said.
D and E.
Oh, D and E.
Yeah,
Four
just to make
figure.
it more
Just to
confusing.
be different. Just to be different. I guess none is the same thing, but they want DNA, they're getting it. Right, now if I wanted to get the mean, isn't that a small enough data set that I could just do it by hand? I don't need to do all that in buttons. I should be able to do it in my head. So 13, 21, 30, 40, 40 divided by 5. Oh, 8. A different data set, another data set. Okay, let's do
This
this
one
one.
got confusing trying to do the median on there.
On
when
this one?
You're telling me, no, the next one.
This one?
Yes.
Okay, let's count the data. 1, 2, 3, 4, 5, 6, 7, 8. Now, when there are 8 numbers, isn't there 2 guys in the middle? Can you see them? There's a 2 in the middle and there's a 3, right? So what's the median when there's 2 numbers in the middle? I think Nadia said it. Is it 2.5?
Oh, that
I'm
makes
sorry.
so much more sense.
2.5.
2.5. Now, at last, there is a mode in this set of data, isn't there? And the most common number, and it didn't happen that common, but it happened more common than anybody else's one. And then the mean is you add them all up and divide by 1, 2, 3, 4, 5, 6, 7, 8. So, you know, you
That
can
one
do that.
tricked me because I was thinking that it had to be a bigger number because we were dealing with 30. So I kept thinking it didn't have a mode. That's so dumb.
Are you okay? Are you okay now, Tara?
Uh,
You good?
yeah,
I mean, you
I'm
figured it
alright
out.
now. I think I got it.
Okay, good. Well, I have one last topic to kind of start with, and you're going to need the calculator for it, and you're going to do that thing, but let's show you the question first. The ones they give are very small data sets, but what I'm going to show you is what you need to do when it's larger data sets. And we're going to get a guy which is called the 5-figure summary. And the 5-figure summary is made up, obviously, of 5 numbers. It's a guy called the mean, the minimum, a guy called Q1, a guy called Q2, a guy called Q3, and a guy called the maximum.
Yeah.
And the guy that's called Q2 has another name. He's called the median. So in a 5-figure summary, you find all 5 figures. And once you've done it, you can then create a diagram called a box plot. So I need some data, and I'm going to use the same data as before. Remember this data here, the ages? Right. We are going to find a 5-figure summary of the ages of people in this class. So close as many windows as I can so I can see what the heck I'm doing. And let's go. It's at this point that you can't avoid using the TI-84 calculator, right? So I'll put it on, it should be on. I'll hit start, I'll do edit, and I'll type in all the numbers. So I have got 65, 19.
We can't see anything.
Oh, thank you for telling me. Can you see a calculator now?
Yes.
Yes.
Okay, so I'll pretend I'm starting from the scratch then, the beginning, right? So you hit start. Choice number 1 is edit. Then you type in your numbers. So you would type in your 65. I know it's there, but I'm starting from the beginning. Then you do your 19. And you keep going until you've run out of all the numbers in the data. And hopefully it only takes a little while to type them in. You have no idea how hard this is for me with my one eye. I am desperately trying to make sure that I don't scan over a number or miss it. I think I'm good. Looks good, right? I got the data in. Now, I'm not doing anything different. I'm doing the exact same stuff that we did to get the mean and median. So I'm going to now move over to calc, choice number 1, and then blue button 1. Now, the 5-figure summary is here, not on this screen, but as I scroll down, you're going to see it. Minimum, Q1, Q2, also called the median, Q3, and the maximum. So I'm writing that guy down. There's a 7 because that was the youngest person. There was an 18.5, which goes here. There's a 28.5, which was the median. We already found that earlier. There's a 36.5 for a guy called Q3. And lastly, there is a 65. So I'm now going to return and see if I can maybe explain to you what some of these guys are. It's pretty obvious, I think, who 3 of them are. But there are 2 that are not obvious. God, that mouse has to get fixed. Would you agree that, I'll have the data here. Would you agree that the minimum of 7 just means the youngest? And that the maximum is me, the oldest? And isn't Q2 the one in the middle? We're pretty comfortable, that's the median. So who on earth is the Q1 and the Q3, right? Well, I want you to imagine, well, not imagine because I'm going to write it down, what this data would look like if I wrote it down in order. So we'd start with a 7-year-old and then the other 7-year-old. So that's them out of the way. The next person was an 18-year-old. Then there was 2 19-year-olds. And I'm going to do my crossing out thing. And then there was a 28-year-old, a 29-year-old, a 31 and a 32-year-old. There was a 41-year-old. There was a 48-year-old. And finally, there was a 65. God, I almost made it, right? 65. Right. There are 12 numbers in this data. The 2 middle guys are there. And that guy there is 28.5. And he was the median, right? We already know him. This guy here is the minimum. We know him. This guy here is the maximum. So where did this 28.5, where did this 18.5 guy come from, right? Do you notice that these guys here, if I rub them out, Do you see there's 5 numbers on the low side and there's 5 other numbers on the high side? Can you imagine that I just basically ignored these numbers, right? Pretend they're not there. What is the middle of these? Sorry, put a little wall here. There are 6 numbers on this side, sorry, and 6 numbers on this side. Right. I was thinking of a different situation. If you've got 6 numbers, where is the middle? Well, whoops. The middle of these 6 numbers is 18.5, and that guy's called Q1. So we haven't ignored this one. And the middle of these 6 numbers is between here and here. And that ends up being where the 36.5 is. So can you see Q1 is the middle of the lower half and Q3 is the middle of the upper half? And forget what I said about crossing them out. You only cross them out if there's one number in the middle, right? That's where my confusion came from. I'm now going to finish off by doing this new diagram.
Q1, middle of first half.
And middle of the second half.
So Q2 is just the medium.
And Q2 is just a median, just another name for it. Now, to create this thing called a box plot, it's a new diagram. You look at your smallest and your biggest. Now, I know it starts at 7 and it finishes at 65, but it's typical to do it in nice units. So start at, say, 0 in this case. And finish at 70. The smallest number is 7. So my best guesstimate is 7 is about here. If you agree, that's roughly where 7 is. And my biggest number is 65. So I make a little mark at 65. 18.5 is probably about here. And 28.5 is about here. And 36.5 is probably about here. So in each one of these, you draw 3 big lines, right? Q1, 2, and 3, and 2 little ones for the min and max. And that is called a box plot. Have you ever seen a box plot somewhere? You ever seen it maybe in chemistry or physics or social sciences or anything? You ever seen a guy that looked like this anywhere? Oh, no. A surprise. They're very common.
And then a huge square there.
So what this fella is doing is giving us a visual representation of all the ages of people in this class. And so you can use it to kind of imagine what the entire class would look like. Well, we're pretending that there's 7-year-olds in this class. So it starts at 7. It's my minimum. Finishes at 65. That's my maximum. Q1 is here. Q2 is here. And Q3 is here. And if you're wondering why they called Q1, 2, and 3, think of it like this. The first quarter is between here and here. The second quarter is here. The third quarter is here. And the last quarter is here. Do you see it kind of, it's a bit like taking your data and cutting it into 4 pieces, right? Where do the first quarter, the lowest quarter, where do the next quarter, where does the third, and finally, where does the last quarter? So calling them Q1, 2, and 3 kind of makes sense. First quartile, second quartile, right? That's quarter of the way along. That's 2 quarters of the way along. That's 3 quarters of the way along. Okay. Suppose I had a scale and it went from 0 to 100 and there's 50 in the middle. And I did a box plot. And this was my class A, and this here was what my class B is. There's a lot of information in these box plots. If I put some numbers on it, so we'll make that 10, 20, 30, 60, 70. Now, which one of those two classes did best in their statistics exam? Should be pretty self-evident. In general, which one did better? Class A or Class B?
It would be A.
Yeah. How do you know? You're right. How do you know it's A? What was the obvious thing to look at?
It went further down the line.
Yeah. You see this bunch here? Isn't this rectangle where most the middle half of the class are? Do you see they're getting scores 50 to 70? Where are this class? Oh God, they're getting like 8s to 12s. See class A, weren't their scores all over the place? Some of them got nothing, some got 100%. And typically around about 60 was the kind of middle typical score. 0 to 25, we had typical score around about 10. So spread out, not so spread out. Did better, didn't do as good. You can look at box plots and they allow you to make comparisons between other classes, between other groups. If this was percentage of the time you were drunk, this would be Scotland. Right? And this here would be Washington State. And so you could look at this and say, there's an awful lot of drunks in Scotland. But there's some Scottish people who don't drink at all, right? And there are some Washingtonians who are drunk 25% of the time. That might actually be true, but whatever. Okay, I think that is a natural finish point. Is there any questions before we close off for today?